Very good morning. Today we are going to discuss about challenges that we have in front of us with respect to data when we use zone architecture. We are going to discuss about that in detail. Right. First of all, how we get data in a software-defined vehicle, from where we are getting it. Software-defined vehicle has cameras, high-end cameras. Those were used in autonomous driving for like lane detection and then traffic signal recognition. For those sort of things, they use those cameras, right? Which generates the data in terms of megabytes and gigabytes, right? That is one source of information, one source of data. And then we have a radar, which is used to detect forward moving vehicle, forward moving objects, right? Then LiDAR for remote sensing, right? And then when software defined vehicle want to display some sort of information to the user, they used to have a high resolution display. Probably it can be a part of your driver information system or navigation system or infotainment system, right? These displays process huge amount of data for animation and then showing the HMI, showing the map, to show the map. For those, they use huge amount of data, right? So summing up all the point, in software defined vehicle, there is an exponential growth of informations or data to be processed by the system. We have huge number of data to be processed in the software defined vehicle for various reasons, right? That is our first challenge. Challenge number two, more traffic. As software defined vehicle is divided into different zones and we have controller in each zones, right? Each one of them process the information in the order of gigabytes or megabytes. Those are exchanged between zones and then from zone to high performance computer, right? With a high speed, right? As there is a huge amount of data exchange in between the zones or in between the zone and the high performance computer, there will be always a huge traffic. First one is huge amount of data. The second challenge is huge traffic that we have in front of us. Third, future proofing. What is future proofing? Usually software defined vehicle network is designed with certain bandwidth, right? Certain bandwidth. They used to design it, they used to architect it. But when the system want to upgrade the software or to flash a new feature, right, or extend an existing feature, in that case, they need to reflash the software in the system using over the air or FOTA, something like that. In that time, we need an additional bandwidth, which is more than the normal default baud rate, default bandwidth in which the system is functioning. So, which leads to a spare bandwidth in the design. So when you design the system, you have to design the system with a spare bandwidth, which helps these things. Remote flashing, right? So software upgrade. This is another challenge in front of us. We have to choose this microcontrollers and then the physical layers and then respective interfaces to meet these requirements. Then in the software defined vehicle, we have diverse devices. Example, cameras, which generates plenty of a huge amount of data, right? That may use certain interface standard like Ethernet, I think maybe like USB, right? Then we have a radar. Radar can have their own bus system interface, right? Probably LIN or RS-232 I2C. Then we have ultrasonics and motor and actuator controls. Those can use CAN. Ultrasonic can be maybe interfaced using I/O ports. Door locks can use a PWM. So each device or each device or sensor associated with zonal module uses diverse bus systems. Some uses just a low speed interface, RS-232 USB, something like that. Some uses LIN, some uses CAN-FD, some uses I/O, some uses PWM. Like that, we have a diverse bus system requirement when we go for these by bus system requirement, which handles data of in different size, right, from gigabytes to a few bytes of information. These are the four challenges that we have with respect to data in software-defined vehicle. What are those? Data, exponential data growth, huge traffic, spare bandwidth, which is future proofing, then diverse device needs, meaning diverse bus interface requirement. So in section 2, we have a typical zone module or zone controller, which is associated with the sensor and then a high performance computer. When it comes to sensor, we have camera, radar, ultrasonic sensors, and then motor bar actuators, door lock. These are the things that we have. These sensors are interface with zone module probably by low speed interface, LIN, CAN, I/O, or PWM. These are the different bus interface options that we have in front of us. Again, from zone module or zone controller to central computer unit or high performance computer, the interface is done using a PCI, peripheral control interface, and then 10 base T1, 100 base T1, or 1000 base T1 Ethernet, CAN XL, which is very newly introduced CAN version. Initially, we have a CAN 2.0 B, then CAN FD. Finally, they have come up with CAN XL, which can handle bandwidth up to 20 megabits per second. Right. With respect to Ethernet, it has its own speed in the order of GBs. Right. We have a detail in this table. We are going to discuss about that. When it comes to PCI, it exchanges the information, right, in the order of, like, they may use a Gen 4 or Gen 5 PCI interface, which can handle bandwidth up to 16 to 32 giga transfer per second. That much high speed can be used right now. So this is from zone controller to high performance PC. Got it. So how they are, from this, what we conclude is the demands or a requirement or the challenges that we have in the software defined vehicle with respect to data is handled, or the challenge is solved using these right network selection and the right physical layer selection, right? These solve the problem. For that only, these are for that only we have these four types of networks like PCIe, Ethernet, gigabit Ethernet, CAN-XL, and then the LIN. Right. Here is a comparison in section 4, which details about which the type of the interface and then what bandwidth it can support, and then the physical layer requirement. Right. With respect to PCIe, it is used for high performance computations, artificial intelligence, sensor fusions, and logging. For these, we can go for it. Bandwidth of this one is 8 to 32 gigahertz transfer per second. For that, we have to use PCI 5, the physical layer which is related to PCI. Then the gigabit Ethernet, it is a backbone to central compute unit. So probably mostly zone controller uses this one to exchange information from the zone to high performance PC, as well as from high performance PC to zone. Understood? So bandwidth of this particular interface is 100 Mbps to 1 gigabits per second. It's in very high speed, right? For that, we have to use automotive Ethernet physical layer. Understood? For the physical layer connection. The CAN-XL, we all know what is CAN in detail. We have a lecture in our channel as well, mastering in CAN bus system, a separate playlist available. You can explore what is CAN there, right? This CAN-XL is an advanced version, very latest version of the CAN, which support up to 20 megabits per second. The earlier one, the basic one is maximum 1 Mbps, then they improved to 5 Mbps. Now it is maximum up to 20 Mbps we can do. Finally, the LIN, which is a low cost version of CAN, right, which has similar characteristic to CAN. It uses single wire communication, and then has been designed by a consortium, right, for a low cost option. Right, it can support the bandwidth up to 20 megabits per second. These are the different choice that we can make to address the challenges that we discussed when it comes to data. Right. Apart from that, we have a service-based architecture in the software-defined vehicle, which is achieved via there will be a standardized buses, one among these four. From there is a standardized software control which connects with the cloud and uploads the necessary detail from the standard bus, right? So these software in the cloud can be validated in the cloud in the OEM bench. Then it can be dispatched via over-the-air method, right? That is what they call as service-based architecture. As we told something called as future proofing. What is future proofing? Having a spare bandwidth, right? By having a redundant path, right? We used to have a foundational hardware setup of hardware implementation. Along with above that, we used to upgrade our software from the cloud via over the air. Right. That is what called as future proof network topology. That means you have a default or a standard bandwidth during your normal operation. When you want to flash a software or renew or an upgrade or implement a new feature, in that time you will use that spare bandwidth, right? So to conclude, what we can conclude, right mix of high speed and low speed network, right? Right mix depends on our need, depends on our sensors. Enables and the right mix of high speed and low speed networks with the right physical layer enable zonal architecture to deliver today's performance and tomorrow innovation. That is like a motto or the final conclusion that we make using this detail. Is it clear? Right. I hope I have given a clear detail about what are the challenges that we have in software-defined vehicle with respect to data and how to fix it, how to solve it, what are the solutions that we have in front of us.